here to learn, but I also serve as one of the deans of this summer school, along with Professors Dana Longcope, who started off this summer school, and Professor Jan Soika, who is sitting at the back. Professor Baker started you off with a wonderful overview of heliophysical exploration. And one of the things I just wanted to add as a footnote to his really great talk was what the author Stephen Pine referred to as the third great age of discovery. Heliophysical exploration has been that. The first great age was the discovery of the continents, led by Columbus. The second great age was the search for the Antarctica, the uninhabitable Antarctica and the deep oceans. Space exploration is really the third great age of discovery. And you heard how inspiring that age has been and continues to this day. Professor Baker was actually in a unique position to tell you about that history because he's also leading at the present time the decadal survey over the next 10 years, which will provide, one hopes, a roadmap, as he just comes in through the door, a roadmap for space exploration as we go forward. So the third age of discovery continues and will continue on, and I think all of you are in an enviable place. The gloomy news that you sometimes hear across the cable channels on budgets notwithstanding, if you look at the cycle of history, science funding has always been an issue that goes through cycles. I try not to think too much about that, though it has enormous implications for what you will do or what we do as you plan your future. But if there was ever a more inspiring time to get into space physics, it is now. You just have to look at the history that he described so well, and this third age of discovery marching on, and many of you will be leaders in that. So keep that in mind, and then there is a lot to discover. My talk actually is very different in spirit than his, even though he emphasized to you how basic plasma concepts is one that underlies all of this. And I really wouldn't have as much of the grand sweep of history here, but a mere recounting of some basic concepts that I think you will find useful as you navigate your way through these lectures. Some common plasma themes. But before I get into that, let me ask, how many of you have had a basic plasma physics course either at a senior or a first-year graduate level? Just a show of hands. Okay, that's significant. To some of you then, some of my material would be too introductory, but I also saw a number of hands not going up. To the experts in the audience, I apologize ahead of time if some of this is repetitious, but I guess it never hurts to see this for a second or a third time, or for the nth time, because even one who teaches learns from that exercise. So the goal of my lecture would be to review a few basic plasma concepts and models that underlie the lectures later in the week. I should point out that there are several excellent textbooks in plasma physics now. This wasn't true when I was a graduate student. There were two. But books have been written, and some of them well known, have been around even when I was a graduate student. But since that time, many have appeared. Book by Chen, by Nicholson, which is sadly out of print, but one of the finest textbooks ever written, and plasma physics, Goldstone and Rutherford, Boyd and Sanderson, and a much more recent one by Belland. The book I am most familiar with is written by Professor Gurnett and myself, and from which most of the material is taken. When I arrived in Iowa some 10 years ago, and I have a Van Allen tale to tell you as well, because I had the privilege of having an office next to Professor Van Allen's for a period of 10 years. And Van, I don't know what he was like when he was young, but by the time I had met him, he was a senior statesman, very mellow and sage-like, always very interested in mentoring and helping younger faculty members, such as myself. So the two things he did every morning, one is to bring his and my own copy of the New York Times from the parking dock where it was left and bring it to my office. So we'd always chat in the morning, start our day off. And the other thing was that he was always full of jokes and humor. He was a real wit, very sharp. I never heard him, didn't waste too many comments, nor did I ever see him sleeping in any colloquium or seminar when people 30 years younger than him dozed off. But a standing joke between him and me was his longevity, and he brought it up every time. I remember one morning I asked him whether he would be available, and that was a day in fall, for a visit by Professor Gerhard Herendel from Germany, which was going to happen in spring. And Gerhard asked me if Professor Van Allen would be around, one of the first things I did. So I checked with him and I said, Van, Gerhard is planning a visit next semester. Would you be around on such and such days? So he looked at me and he said, at my age, I don't buy green bananas. So about 5 days before Gerhard comes, just check that I am around. This was typical of him, always hinting at his own mortality. So when he actually passed away, and he never slept in talks, he was sharp as a whip till the very last day. Not that I was around for the last day, but I can only imagine. If you walked into his office, it was strewn with the kind of history that Dan talked to you about. And then it finally happened. I had a hard time believing that he had actually gone. Still very much around as a presence in my life anyway, by the sheer inspiration he gave so many of us for so many years. Never moved from Iowa, despite many offers to him worldwide. And I think he was a little disappointed that I left when I did. He almost thought it was a break of loyalty of sorts. We had a magnificent 10 years, not the least of which was because of his presence at the University of Iowa. So Professor Gurnett was in Iowa, and we wrote this book together. It was one of the things we got done, and the book has several flaws that I know about, that I've tried to persuade Professor Gurnett about as well, and together we'll write a second edition soon. So I hope the second edition will be better than the first. I will begin with the definition of a plasma. A plasma is an ensemble of charged particles capable of exhibiting collective interactions. This is the most general definition of the plasma. So clearly hinted in this very definition is the notion that you cannot just think of the plasma as individual charged particles, because they do something more. They exhibit collective behavior. And so there are levels of description of a plasma, from this very simplest to the more collective as we move forward. And it gets more difficult as we do so. Already the difficulties are fairly manifest at this level. Here there are surprises as well, but especially so in the kinetic regime, where there is a lot to learn. So the first and the simplest level of description is where you look at single particle dynamics in prescribed electric and magnetic fields. The word prescribed should be emphasized here, because what we're really saying is that the electric and magnetic fields have been given, and charged particles move in them. What we are not addressing at this level is how the movement of charged particles is itself a source of electric and magnetic fields that change whatever it is that we might have prescribed. So in the first level, we will ignore that feedback effect, if you will, but not for long, because plasmas can be viewed as fluids, as neutral fluids can be, moving in 3D space under the influence of what we call self-consistent electric and magnetic fields. And here it is that you first recognize the importance of the word self-consistency, because what that means is that the motion of the plasma particles as fluids have an effect on the electric and magnetic fields that you might have prescribed initially. But as the movement occurs, these evolve in space and time. And keeping track of that is the challenge of plasma physics. For those of you who have taken a course in electricity and magnetism, you know very well that Maxwell's equations, amazingly, like Schrodinger's equation in quantum mechanics, are linear equations in electric and magnetic fields. If nature were, therefore, as simple as linear equations, we would have solved the problems of plasma physics a fairly long time ago. Why did we fail yet? We succeeded in many ways, but there are still unsolved issues. It's because, as you know, in Maxwell's equations, there are source terms. And these source terms are the charge density term in Coulomb's law or Poisson's equation, or the current density term in Maxwell's equation. These are the sources of nonlinearities in plasma physics. And it is the prescription of these source terms and their solution that make plasma physics a harder problem than solving Maxwell's equations. And you will see that repeatedly. And this is this word self-consistency that comes in through the source terms that we will talk about. And then you can go to a higher level of description where you're not even looking at the plasma as a fluid in configuration space, but you're looking at a plasma as a kinetic fluid in mu space. This is something, this notion is from statistical physics, where you have the x space, the configuration space, having 3 axes, and the velocity space having 3 additional axes. So that makes a 6-dimensional space in which you actually track the motion of charged particles. You calculate what charge distributions they produce, ones that enter Maxwell's equations, or what currents they produce. And these are self-consistently coupled to Maxwell's equations. It is this requirement of self-consistency, or the nonlinearity in source terms, that makes plasma physics, space physics, plasma astrophysics a complicated subject with open questions. And the mathematics that describes them has in fact the same sort of parallel. If you go to the theory of differential equations, despite surprises, you will see that linear theory has a lot of practical, well-solved issues already done. It's in the nonlinearities that we have very many open questions. So a lot of the unsolved difficulties in plasma physics and space physics are nonlinearities. We'll get into that more. So I begin then with the simplest level of description, the single particle orbit theory. And the beginning equation is in fact Lorenz's equation, the non-relativistic form in which mass has been extracted out of the momentum term on the left-hand side. And on the right, you have prescribed electric and magnetic fields. For much of the talks in this summer school, you won't have to worry about relativistic particles, but you could treat relativistic particles by simply moving m inside this differential operator, where m now is not just a constant quantity, but is a relativistic mass, and there has to be integrated per se in that matter. But let me deal with this, because this will cover the dominant phenomenon that you would learn about in this summer school. And a very useful notion is the notion of the guiding center. The charged particle in a straight magnetic field generally undergoes helical orbits, and here you see the manner in which a positive charge moves in a pure magnetic field. It has a Larmor radius rho c, and the guiding center is a fictitious center of orbit. The particle itself is not at it because the particle is moving in this helical orbit. But the guiding center is a very useful notion or concept that really follows the field line, and we will be using this idea of the guiding center throughout in our discussion of single particle orbits. So this should be very familiar ground to you. The Lorentz force law, the V cross B term without the electric field, actually gives you helical orbits around a uniform magnetic field. What happens if you complicate that picture by introducing a constant electric field? Consider in particular a constant electric field E and a constant magnetic field B, and for simplicity, we will actually treat the E as if it is entirely perpendicular. Because if there is a parallel electric field, then you can very simply write an equation that you understand well, which is M dV parallel dt equals QE parallel, where parallel represents the component of E parallel to B. And you know how to solve for that. That will just give a parallel acceleration to the charged particle, to the guiding center, moving parallel to B. The part that is a little unusual is what the perpendicular component of the electric field does. And what it does, and you can show it exactly from this equation, is that in fact it introduces what is called a drift, the first important drift that you will learn in plasma physics, which is E cross B over B squared. And I'll show you a picture of this right away, but notice an interesting thing. This particular drift doesn't depend on the charge. So ions and electrons both drift with the E cross B drift and under these conditions, and that does not produce a charge separation. This statement, though, is not true if the plasma has a strongly collisional and neutral component, as Professor Soika will talk to you in his last lecture of the series. So the statement that the E cross B drift produces no charge separation is true in a fully ionized plasma, but not true in the ionosphere. There are always exceptions to statements that sound absolute, and that's one exception. But nonetheless, getting back to our picture, here is an electric field that is in the Z direction, the magnetic field in the Y direction, and E cross B is a drift in the X direction. So the guiding center then, despite the fact that charged particles move in opposite directions and you have a charge-dependent helical motion, the net drift itself for both these charged particles occur in the so-called E cross B direction, and that shows here. Now, if VE is perpendicular to E, then E dot VE is actually 0. So if the electric field is stationary and curl E is 0 according to Maxwell's equation, and you can define an electrostatic potential, which is the gradient of phi. So if V is perpendicular to E, since gradient of phi is perpendicular to E, V must lie in surfaces of constant electrostatic potential. And this is what this picture shows. E is pointing in this direction. These are surfaces of constant electrostatic potential, and the E cross B drifts along those surfaces. Okay? It's also a consequence of the E cross B drift. Life doesn't stop at that. We were dealing with a very simple kind of a electric and magnetic field with E constant and B constant. Most interesting fields, magnetic fields in nature, certainly in the heliosphere, have spatial dependency. So in fact, if you have a unique magnetic field which has spatial gradients getting stronger to the right, you can sort of qualitatively see that the Larmor radius is not going to be uniform in fields like that. In a uniform field, of course, is constant and the particle orbit winds back on itself. But if in fact a particle is moving in a spatially non-uniform field, the Larmor radius is going to shrink where the magnetic field is actually stronger. And therefore, it's a larger radius here because a smaller radius there. And you can sort of see how you would have motion of this form. And in this particular case, and this is not an exact solution of the Lorentz equation, but in fact, it's an approximate solution in the limit in which the Larmor radius is small compared with the scale length of the spatial variation of the field. If that number is small, then you can write down the guiding center drift by essentially imposing some perturbation theory on the Lorentz equation, and you will get this result. I'm quoting results. The proofs are actually given in more than one textbook of the kind that I have already cited, but these at least will give you the facts that you have a gradient B drift, which is B cross grad B over B square multiplied by W perp over QB. This is the perpendicular kinetic energy represented by this number here, QB, Q being the charge, B being the magnetic field. Unlike the E cross B drift, the gradient B drift can in fact produce drifts of electrons and ions in opposite direction. In so doing, therefore, gradient B drift can produce currents. And you will see this plays an important role in the production of the ring current in the Earth's magnetosphere, something that I'll get to in just a minute. You talked about the gradients of magnetic field there. Now we are referring to a different behavior of magnetic field, which is also true of many naturally occurring magnetic fields, is that they have curvature of this kind. And the radius of curvature points towards the center of this curved magnetic field, and you can write down a curvature drift, which can be again shown from guiding center theory to be given by 2W parallel by QB square, RC cross B by RC square, where RC is this radius of curvature. Now, of course, this parallel magnetic field is half mv parallel square. For vacuum fields, it turns out that V curvature and V gradient can be combined in a nice nifty form, which really can be represented by either. This is often done to a first approximation when one is trying to simply work out the orbits in the Earth's dipole field, and it underlies many calculations. And here is what I was talking to you about just a minute ago, about how, due to the presence of these drifts, you actually, to leading order, have, in fact, the ring current contribution. So this is an oblique view of the ring current of this, the ions and electrons. As I said, this is not produced by the E cross B drift, because the E cross B drift doesn't produce charge separation, as we just emphasized. But the gradient B and curvature drifts do, which is why the ions and electrons are showing opposite drifts. And these, in fact, when you add them up and calculate a current density, gives you a net ring current in the Earth's magnetosphere. This then relates the single particle drifts to something that is quite observable and practical in the Earth's magnetosphere. Going away from the drifts, and I want to introduce the concept of adiabatic invariants. One of the things that I'm going to try to do as I proceed in this lecture is that to connect up the knowledge of plasma physics to the larger life of physics, because one of the things that you will all encounter as you will go into your careers as space physicists or as heliophysicists is that sometimes the language of plasma and space physics is not assimilated as well in physics departments as it should be. And I'm not exactly sure what historically is the single most important factor that contributed to what I call this level of alienation that you sometimes see. In engineering departments, it's actually one that has been more receptive. Plasma physics, being a fundamental and an applied physics field at the same time, sometimes has fallen between the cracks. But at least one part of the failing we as plasma physicists should take responsibility for is that we have not always done our best in taking the concepts that are really important in our field, which I submit have great fundamental value, and assimilating them in the larger mainstream of physics. But in plasma physics, you have seen develop some of the critical ideas of chaotic dynamics, for example, the field of chaos, which has been such a dominant development in the 20th century. And it's amazing that we take that body of knowledge for granted without necessarily acknowledging that much of it actually came from plasma and space physics. So adiabatic invariance is something that plasma physicists have made a lot of use for, but it actually goes back to Albert Einstein. He was in the Solvay conference in 1911, and somebody actually asked him this question, and believe it or not, he produced a very subtle and correct answer to the question within a matter of minutes. Somebody actually asked him that if you actually have a man who has a simple pendulum, and everybody knows that the period of this pendulum, simple pendulum, is 2 pi times square root of L over G, where L is the length of the pendulum and G is the acceleration due to gravity. The question that was posed to Einstein was that if somebody would just slowly pull up the length of the pendulum, very slowly, while the pendulum was undergoing many oscillations, what would anything be constant? Well, surely the energy would change, the frequency would change, but Einstein immediately suggested that the ratio of the energy E and the frequency nu would remain approximately invariant if the length were gradually shortened. This became later formalized in the life of physics as adiabatic invariant, adiabatic representing slow change, and in Hamiltonian mechanics, this got formalized through this equation of the harmonic oscillator. If in fact omega square is a constant, from freshman physics you know how to solve this equation. The problem of the simple harmonic oscillator is in part the exercise of actually slowly changing the frequency, right? We already said that if somebody up there slowly changed the length, you knew that the frequency is going to change because the frequency or the time period is given, the period of the pendulum is 2 pi square root of L over G. G being constant, if L changes slowly, of course omega changes. But what we now know is that the adiabatic invariant is J, which is actually the so-called action of this classical orbit. Here it is in P and Q space. If you look at what Hamilton and Jacobi did, they actually showed that these are in fact exact constants of the motion. All right? If you didn't vary frequency. One could show that from Hamiltonian mechanics. And what is J? So for this particular simple harmonic oscillator, you could set up a simple two-dimensional phase space, Q being like your X, P is X dot over M, or Mx dot, pardon me, I misspoke. P. So if you draw a little orbit, typically the orbits are elliptical if the pendulum is going back and forth. Hamilton and Jacobi showed that P dq, the area under that orbit, is in fact an exact constant of the motion. What we now know in adiabatic invariant theory is that not only is that an exact constant of the motion, but if you should change the frequency very slightly as a function of time, slowly, so that epsilon is a small one, J of course is no longer an exact invariant, but it is in fact an adiabatic invariant. That is, J changes, but much more slowly than some of the other things in the system, such as the frequency itself. And the variation in J over many orbits, delta J over J, is a number which is exponentially small. Exponential minus C over epsilon, C is a positive quantity of the ordered unity. When epsilon is small, that means delta J is varying. Think of that exponential function. It's going to have very, very slow variation. Finite, but very, very slow. And slower than any power series. So this is what is meant by saying invariance to all orders. And this is critical because the magnetic fields in the radiation belts that Professor Baker talked about can be quiescent, can be slowly varying, and particles are often confined in them. Why are they confined? And they have to be confined for multiple orbits. If you just had this constant varied for one, but invalid for 1 million orbits, then you would not confine particles very well there. What saves you is this adiabatic invariant, which tells you that the mu invariance that I'm coming to, the adiabatic invariants, all vary much slower than any power law, goes like exponential. Let's talk about this adiabatic invariance now. Are you all with me? Any questions so far? Feel free to interrupt me anytime in anything that you don't understand. This particular idea that is invariant to all orders was understood precisely mathematically many years after the notion of adiabatic invariance itself was written. And there's a whole mathematical literature on this that continues to this day, trying to quantify for various Hamiltonian systems how rapidly adiabatic invariants actually change. Now, for charged particles in a spatially varying magnetic field, here there is the region of strong magnetic field. This is a region of weak magnetic fields where the magnetic fields are much more separated. And this is sort of laying it out in one, in a simple sheet of paper, what the Earth's magnetic field actually does. If you look at the dipole field of the Earth's magnetic field, it's really strong at the two throats that are polar and weaker near the equator. This then is a representation in the simplest form of a charged particle motion here, and what you're going to see here are three types of motions, okay? One is this very rapid cyclotron motion that you're aware of, the helical motion that simply goes around a strong magnetic field. Great. That is in fact the fastest motion, what we call the cyclotron motion. Then there is a parallel or bounce motion, and I'll make this more precise to you in just a moment, where the particle just goes back and forth. That too has a periodicity to it. And the third is the gradient and curvature drift that goes around like this, which takes the longest. So you really have three types of periodic motion in this very simple mirror magnetic field. And those are the three types of motions that you're also seeing in the radiation belts. These ideas are very important to Professor Spritz's talk, pardon me, that will come a little later in this week. Associated with each one of these periodic motions, you have three adiabatic invariants. The first one is called mu, which is the ratio of the perpendicular kinetic energy divided by the magnetic field. So if the rate of spatial variation or the temporal variation of the magnetic field is much smaller than the cyclotron period, then this is an approximate constant of the motion that is valid for many, many orbits around the magnetic field. The second adiabatic invariant is J, written as such, mv parallel ds. This closed line integral represents the periodic orbit going back and forth. And the third adiabatic invariant is the flux enclosed by that orbit as you're going around. Adiabatic theory tells you that all these are constants to a very high degree of accuracy, exponential minus c over epsilon, where c is a constant, epsilon represents the slow variation. So, I want to go back. I don't want to quickly transit. So if you go back to this picture then, I want to tell you about the parallel bounce motion. So you have the magnetic moment, mu, which corresponds to this rapid motion, W perp over B. So B is weak here, and W perp is of a certain value. As you move further down, B gets stronger, W perp, therefore, goes up. Now, if the kinetic energy of the particle is a constant, which it is, right? That's a pure constant in motion for spatial dependent magnetic fields here, or time dependent because the magnetic field by itself does not change the energy. Then what you have is half mv perp square plus half mv parallel square, always adding up to a constant. But v perp square part is going up as you're going near the throat of the magnetic field. What that means is that the parallel part of the energy must go down. So if the B increases rapidly enough, you will therefore confine a large number of particles for which V parallel will be reduced to 0 before you get to these throat points. Those are then the trap particles. Those are, in fact, the very particles that you also see in quiet times that are confined in the radiation belts. I say quiet times because if you have certain types of wave activity during storms or other disturbances of the kind that Professor Baker talked about, you can show from nonlinear chaos theory that you will start breaking these invariants. And you can, in fact, lose particles from the radiation belt. That, in fact, is a whole new line of research that goes on in space physics, the chaotic motion of charged particles that I don't have the time to go in, but it all fits into the overall framework of chaos theory, which, as you know, as I was pointing out to you, is a fundamental activity of many physicists, theoretical as well as experimental. And be assured that some of the most important developments in that theory actually came about from plasma and space physicists who are worried about either the orbital stability of planets or the confinement of particles in complicated electric and magnetic fields, spatially and temporally varying. I now want to go on to the kinetic description of plasmas, which is in fact the third level that I was talking to you about when I introduced the various levels of description. And I'm doing this in a way, again, to set you up for some of the lectures where some of this material will just be used without necessarily telling you where they come from. So for those of you who have taken a graduate course in statistical mechanics and kinetic theory, this is, in fact, another very fascinating chapter in the life of physics. How many of you know about the Boltzmann equation in kinetic theory? Aha. So, okay, fewer, but that's a great story, as you know. Boltzmann was the first person who actually studied the evolution of simple systems which were in thermodynamic equilibrium away from such equilibrium cases. Most of the time, life in space is much more traumatic than the kind of simple thermodynamic equilibria that we read about in textbooks. But Boltzmann was a pioneer because he worried about that problem. He worried about how to define entropy when you're not in a thermodynamically equilibrium state, and obtained a really important result called the Boltzmann's H theorem, which in my view is one of the intellectual milestones of 20th century physics. It's in fact buried on his gravestone. If you ever go and visit it, you will actually see that engraved, the formula for the so-called H theorem on his gravestone. I went and visited it. And it was a pretty inspiring thing to do. So he got a lot of criticism for doing that, but it has stood the test of time. So a lot of what we are talking about here goes back to the classical work of Boltzmann, but plasma and space physicists have refined that much further for describing the interaction between charged particles. When Boltzmann was doing the problem, he was essentially using neutral gas, and that was where he derived some of his collision operator from. Plasma and space physicists have done much more because they have to deal with Coulombic attraction or repulsion as the interactive force. So that, as you know, is an infinite range force. So the distribution function of Boltzmann is F, which simply is the probability of finding particles in this so-called six-dimensional phase space in a small volume around R and V. If you integrate F over all of phase space, you get the total number of particles. A classic example is the so-called Maxwell-Boltzmann distribution function, which can be written as, which all of you know, I'm sure, is this average density n exponential minus the kinetic energy mv squared over 2 divided by the thermal energy. K is the Boltzmann constant, and n0 is the number density. If you don't have any collisions in the system, then that equation F, from simple continuity considerations, obeys this equation. Okay? This is an equation which is widely used for the study of instability dynamics in plasma physics. S here is the species, electron or ion, if you're just dealing with a hydrogen plasma, but if you're dealing with oxygen, nitrogen, whatever it is, You will add those species in, and each one of them, and that's the important point, obeys this equation in phase space. In the presence of collisions, you would need to modify the right-hand side of the equation by putting a collision operator. This is what Boltzmann did. He actually calculated for binary collisions the interaction between molecules which have very short-range forces, nearly hard balls. And he derived a collision operator, and he proved a beautiful theorem called the H theorem, which actually discusses the relaxation of any distribution function that you might start with to a unique final state, namely the Maxwell-Boltzmann distribution function. And the picture that we have today, yes, Phil. Indeed. Thank you, sir. This is V dot del F del R. There's a typo. T, my mistake. Thank you, Phil. It'll be corrected again. I don't know how I let that sit for quite some time now. I'm not very good at finding my own typos. So did you get Dr. Judge's comment? This should be an R vector. This is a typo. It's not even dimensionally correct with T. So the picture that you're looking at is that Boltzmann's equation very pictorially simply is a bookkeeping ploy tracking, this is your phase space, okay? XR, VR, think of 6 such axes in phase space, which I can't obviously draw. And you're keeping track of particles that are in this phase space. Now, if they don't have any collisions, they just stay as a kinetic fluid moving around in mu space that you're all familiar with. But if there are collisions, then either particles can leave the volume or can be thrown in because of binary collisions. And the collision operator then corrects for that sort of a thing. So this is the picture. So what does a kinetic problem look like? Suppose if you say you wanted to discuss electrostatic waves. Well, forget about magnetic fields for the moment. Even the problem of electrostatic self-consistent evolution is not an easy problem. And I illustrate the problem for you here. Here I have it right, V dot del F S del R, where R is this displacement vector, and this is del del V. Notice there are all the derivatives present in time with respect to the displacement vector and the velocity vector. And the E plus V cross B term, I put B equal to 0. And simply using electrostatics. Curl E is 0, E is a gradient of a scalar potential. That is what is sitting here. But now, remember, E itself obeys Poisson equation. Del dot E equals 4 pi rho, much beloved by you from electricity and magnetism class, but rho is an integral over F. As soon as you have this complication of the source term, what was a very solvable problem immediately becomes an integral differential equation, quite nonlinear, and life is hard. So this is what I meant by saying the complexity of space and plasma physics. It all comes in through these space terms. And if you, of course, add on magnetic fields to that, you have to deal with vector potentials and all of that. And you've got these closure equations that make life hard. Okay, nonetheless, people are brave. This is, in fact, an interesting kinetic problem formulated in all its rigor. And not able to solve that problem rigorously, people take recourse to approximations. One of the things that Dr. Spritz is going to talk to you about is the diffusion of particles in radiation belts. When he describes RBSP, you need to understand that he's going to show you a diffusion equation, and you're wondering where that came from. Well, when it came from was this Vlasov equation, okay? And unable to solve the problem in its full glory, what people do is to divide up the distribution function into a mean part, either spatially or time averaged, and a rapidly oscillating fluctuation part. If you average both sides of the equation, you get an average f of s. This will cancel out, and you, by definition, you get average of fs1 equal to 0. So that's just definition, and this is typical of what happens in mean field theories. You take a quantity, break up into a mean quantity plus a fluctuation, and then what you do is that you go back and average the original equation, okay, this equation. When you do that, you can hammer that equation as shown in the textbook. into something like this, which looks like a diffusion equation, where D now depends on the wave fluctuations. So the equation that Dr. Spritz will show you is in fact this equation. And it comes from starting your Vlasov equation, dividing it up to mean and fluctuation, and averaging it. And then what people do, and a lot of radiation belt modeling, is essentially measurement of this diffusion tensor by looking at all the wave fluctuations, either theoretically or experimentally calculated. D is represented in terms of those fluctuations, plugged in to figure out how the distribution function actually evolves in space and time. Okay? And people have a whole industry of this. People write huge codes based on it. Beware, though, that is all based on this so-called quasi-linear diffusion equation, which is open to serious questions. People forget that sometimes. They just continue using the equation to make predictions, but quasi-linear theory is a very approximate theory. And one of the great things that you could do for your thesis is to go back and investigate when you do not believe this equation, because it breaks down many, many times. Just because it breaks down doesn't mean we have a very good substitute for it. That's where it takes more work, the refinements of stuff, but there's a lot of problems there that you will do. And I think that these sorts of things are buried in the Spritz lecture as well as the Soika lecture that I want you to be on guard about. One of the things that I want to emphasize to you repeatedly is don't take any equation in any space physics text as gospel. There's usually stuff assumed, made in deriving of the kind that I'm going through that you need to be very wary of, and you don't want to start using these things as formulaic things that you don't trace back to where they come from. Because sometimes nonsense can produce nonsense. Nonsense input in a code will give you a nonsense output because the basic equation is flawed. Beware. So learn your plasma physics well. Okay? I'm going to talk about now fluid models and a very popular model which is magnetohydrodynamics, which underlies so much of global predictions. One of the things that we space physicists do is to rely a lot on global models. You have to realize how primitive these models can actually be, whereas they capture global features very well. They often fail near narrow but vitally important regions, which we call boundary layers. The problem of reconnection is replete with that. The problem of shocks is replete with that. And you need to abandon some of these approaches and do better, more microscopic physics in those layers. That should be as much part of learning. Now, this actually treats the plasma as a single fluid without distinguishing between electrons or protons. This is a severe limitation of MHD that we are getting away from gradually as our knowledge becomes better. Moving under the influence of self-consistent electric and magnetic fields. It can be derived from kinetic theory by taking moments, that is, you integrate out. Remember, we were working in mu space when we were doing kinetic theory? What you will need to do is to go to a coarser level of description, where you'll just integrate out over all of velocity space, so that you're left with only the configuration space and time as the space you will move in. That's fluid-like. That's where neutral fluids live in that. MHD lives in that. And you make some very drastic approximations, some of which I will point out. The very fact that electrons and protons have a distinct identity in the magnetosphere gives a lie in part to the MHD model. I love the MHD model for its mathematical elegance, but beware of its limitations, because it's been quite clear, certainly from studies of the Earth's magnetosphere, but it's also true in the sun, that electrons and protons often behave very differently. You cannot see that in the large scale in an MHD model. Okay? What are the MHD models? They're a beautiful set of equations, and what is really great about the MHD model is that despite the many limitations that I'm telling you about, it's been amazingly successful. It's been amazingly successful outside of a strict domain of applicability. This does happen in physics more often than not. And so therefore there's no question that the MHD model has had great use too, particularly for describing motion on the large scales. Its failure has been over the narrower regions, and one cannot dismiss those narrower regions as things that don't matter, because those narrow regions where they fail, where kinetic effects are very important or two fluid effects are very important, are also coupled to the global scale in a very interesting way. It's not only possible to say something is totally global or something is totally local, because the coupling of the scales is precisely where a lot of the interesting problems lie. This is why this is a multi-scale environment. And you will hear that word too, talked about in space physics quite often. So the fundamental equations of MHD are Newton's law, F equals ma, that you know, and that F equals ma essentially becomes this equation in MHD. Momentum on the left-hand side, the Lorentz force on the right-hand side, and the pressure. To this you could ask gravity, which is a very powerful moving force for the sun as well as for stars, often neglected in studies of the Earth's magnetosphere because J cross B and grad P are so much more dominant. But it's not neglected, for example, when you do atmospheric hydrostatics for the Earth's atmosphere, but that's in fact a very important force. So I've just, for simplicity, dropped it here. This DDT operator here is actually more precisely written as del del t plus v dot grad. This is the difference between a Lagrangian and an Eulerian picture, as you know. Why I emphasize that is because this term hides an important nonlinearity. V dot grad v, the product of velocity terms, which is extremely puzzling and produces all kinds of consequences for MHD as well as fluid physics. Then you have Ohm's law, E plus V cross B equals eta J, or if in a moving frame it's just E prime, eta is the resistivity of the plasma, and you have the self-consistent Maxwell's equations. These are the equations that you study together in MHD. I haven't written here a pressure equation for pressure that would complete this equation, but I want to explore some of the other consequences of the MHD equation, and I'll talk about the pressure equation in just a moment, is that if you combine Maxwell's equation and Ohm's law, what you should do is just go back to this equation, take the curl of it, curl of E plus curl cross V cross B equals eta curl cross J. Assume for the moment that eta is a constant. Then curl of E can be replaced by minus del B del T, and the curl of J you could calculate from this equation. And if you do that, then you can derive, in fact, following these steps, a simple diffusion equation for B, where sigma is the conductivity, or you could write it as resistivity by writing it as eta on top. Eta is typically a small number for most heliophysical plasmas, except the densest and the coldest. And in the limit in which eta goes to 0 or sigma goes to infinity, you have a very interesting problem here that I want to put you on guard about. It is that, notice that the spatial derivative on the left-hand side is a single derivative, a single spatial derivative, right? Whereas here you have two spatial derivatives. If you take the limit of sigma going to infinity and just drop this term, right? You could just say multiplied by a small term. Why can't we just drop it? You run the danger of being terribly wrong at times. And I want to illustrate that by writing out a simple algebraic equation for you on the blackboard and telling you why you need to be careful. Suppose if I have a simple equation, epsilon x cubed plus x squared minus 1 equals to 0, where epsilon is a small positive number, not smaller than 1. That's a cubic equation in x, right? But this is a very curious equation, right? Because there's a small parameter that multiplies the highest power in the equation. Suppose if you say the small parameter is so small, you have to drop that term. What happens? You get a quadratic. Square minus 1 equals to 0. How many roots does the quadratic have? 2. What happens to the third root of the cubic equation? You lost the root. Something violent happened when you went and simply put that root to 0. And the truth of the matter is, this is what is called singular perturbation theory. That is, that in the process of simply dropping this term, you actually threw out a very large root that could scale like 1 over epsilon, for example, or 1 over square root of epsilon, that simply does not capture. This very simple illustration where you're losing a root is what you need to keep in mind when you're doing these classes of problems. Because you have second derivative in space, so sigma goes to infinity, just drop this term, right? Aha, but you've dropped the second derivative, the highest order term in the equation. That's what tells you, be careful. The mathematics of these sorts of equations is called singular perturbation theory, and the whole subject of asymptotic analysis was designed to deal with problems like these. For example, for the reconnection problem that you will hear about plenty, both in my lecture tomorrow and Dr. Dorelli's lecture today, this term plays absolute havoc. In fact, it is not present in ideal MHD at all. And what happens is that this term produces extremely important effects in a very narrow region, the so-called reconnection layer, where very many interesting things happen, not described by ideal MHD. The other thing that I want to point out to you about MHD equations is that one of the weakest points of MHD theory is, in fact, the equation of state. We typically, in all global MHD description, assume that the entropy is a constant, P over rho gamma. This is derived from very restrictive assumptions. Gamma is a 5/3. People's attempts to measure the ratio of the specific heats in the Earth's magnetosphere rarely ever produces 5/3. In fact, deviations from it are well documented in the literature. And how to deal with pressure, which is most of the time not a scalar. It's in fact a scalar when the distribution function is Maxwellian, which most of the time is not the case in space, is another open question, and it's a big open research question that you will deal with. Oftentimes when people do stability studies, they begin with steady state solutions, steady state static solutions, where you would set del del t equal to 0, and you will see it set v equal to 0. Then one obtains this very simple equation, and here I've restored gravity where it can be important. In the version that I showed you earlier, I didn't, but I was telling you also at the same time that this could be really important. In fact, you know, in stars, gravity plays an extremely important role. Rotation is rarely 0. So these sorts of assumptions of static equilibria all have very many exceptions to the rule. Keep that in mind, but is often the starting point for stability calculations. And one of the things that I want to mention to you are the kind of instabilities that a system might have. I mean, if you have a little ball sitting in a cup, and the ball sits at the bottom, and you just give the ball a little bit of a push, it goes back and forth at the bottom of the cup, and gradually relaxes down again to the bottom. That's an example of a stable equilibrium, because the equilibrium was with the ball sitting at the middle, and you give it a little perturbation and it returned to it. It didn't move away from it. But if you invert the cup and put the ball on top and give it a little push, it rapidly moves away from it. That's an example of a mechanically unstable situation. A plasma, too, is capable of being both in stable and unstable equilibria. Most equilibria that are naturally realized in nature are perennially in a state of motion. And the two sources of free energy in the system are in fact the current density, J, and the plasma pressure gradient. Current-driven instabilities are called kink modes because they tend to kink a plasma column. These are very broad terminology, and there are clearly exceptions to the rule. When you have pressure-driven instabilities, they're often referred to as Rayleigh Taylor interchange or ballooning modes. Rayleigh Taylor is a classic instability of a light fluid on top of one. Most of you may have played this game in high school one way or the other, at least I did once. You put water slowly, and then you put dense salt solution very, very slowly onto the water, so you can maintain a heavy fluid on a light fluid for a while, and if you put an egg in, it'll come and just sit right in the middle, because it sinks to the bottom. It floats on top in one case and above the other. So anyway, be that as it may, if you perturb that surface, though, you rapidly see an instability develop, mixing the whole column up. This is the classic Rayleigh Taylor instability of a light fluid supported on a heavy fluid. And what I want to tell you is that the Earth's magnetotail, and this has got to do with Dr. Donovan's lecture on substorms that you will hear. You'll hear about this instability, and he will talk to you about the importance of reconnection and the importance of ballooning instabilities or interchange instabilities. They're basically of the Rayleigh Taylor type. So let me take some time to explain this to you, that you have curvature and gradient pressure. Curvature sort of takes over the role of G, of gravity. You know, it's like a virtual acceleration. Imagine particles that are winding around these magnetic field lines. They're sort of going to feel a centrifugal force, if you will. A centrifugal force is like a G. So what did you learn in the previous picture? That if you have dense fluid against a light fluid, against the force of gravity, that's unstable. Here too, this is called a bad curvature region because the plasma pressure, imagine that the gradient is pointing inward and the curvature is this way. So gravity is pointing that way, right? It's like minus G, right? So this is going to be unstable. Why I'm saying this to you is because plasma supported in this manner has a propensity to become unstable to a Rayleigh Taylor type of mode, which is called ballooning or interchange, which Dr. Donovan will introduce to you. And here you actually see this. This instability is called by various names, interchange ballooning, but Eugene Parker introduced this for molecular clouds, and is also known as the Parker instability in astrophysics. That if you have magnetic field lines which have a gradient of density and a gravity, the curvature, G takes the role of curvature here. So you set up this nice equilibrium, but this is really unstable. And here is a simulation of the kind of instability the system develops. It develops this mushroom type of caps. When you were looking at that Rayleigh Taylor things, you saw these little things going, multiple numbers of them. And what I'm really doing here is to showing you pictures of them as they come out from an MHD simulation of a Rayleigh Taylor type of instability. And they develop these sorts of characters. And this is something that plays a very important role in numerous situations, both in the Earth's magnetosphere and in Jupiter's magnetosphere. Okay. I want to talk to you about some very simple concepts of magnetic reconnection here in this introductory lecture, but there'll be a much more elaborate lecture on this later on. But I want to talk to you about this frozen flux or field theorem, which is one that Hannes Alfvén derived. As many of you know, Hannes Alfvén is often regarded as the father of MHD theory and the only plasma physicist who ever won the Nobel Prize. There is a joke in the world that it is because he was also a Swede that the Nobel Committee decided to reward him, but this I think is grossly unfair. If you look at what he has done, it's really phenomenal for the field, so he fully deserves his Nobel Prize. But there's been no other Nobel Prize winners, though many have been nominated. What Alfvén's theorem is what happens in a completely ideal plasma where there is no dissipation. So if you have a circuit in plasma that you draw, imagine a red dye or something that somehow you could paint on the plasma fluid, and that's evolving as a function of time. As it evolves for a very short period of time, this circuit will deform and become C2. Alfvén's theorem simply says that in an ideal plasma, the flux contained in this circuit is going to be a constant for all times. This is not true if the system has a little bit of diffusion or resistivity, but it's true if sigma is truly infinity. Okay? Another form of Alfvén's theorem is, suppose if you have a field line and you locate two plasma elements on it, then track how that field line deforms when you follow the MHD equations. Well, this field line becomes straight initially, will quickly become curved, but Alfvén's theorem also says if there are two plasma elements sitting on the field line at time t equal to 0, and if the plasma motion is ideal, it will remain on the same field line for all times. like beads on a wire. They never leave the wire at all. They're always tied to field lines. And that E cross B drift that I introduced to you for the single particle drift is the drift with which all electrons or protons will be tied to field lines. That's in fact completely consistent with Alfvén's theorem. So that's what happens if E plus V cross B equals 0. But if on the right-hand side you have a term R, the curl of which is non-zero, eta j is a good term for that, then Alfvén's theorem is violated, and you get magnetic reconnection occurring. As I said, you'll hear about this in Dr. Dorelli's talk, and I'll elaborate on the consequences of magnetic reconnection more. But this is what happens when you get magnetic reconnection going, is that field lines come in, the red and the blue lines merge, break up, and go along in opposite directions. This sort of process is forbidden in ideal MHD, but permitted in resistive plasmas. This material that I talked about, MHD, kinetic theory, all of this shows up in one form or the other in all these lectures that you're going to talk about. These people will not have the time to tell you about the origins of MHD theory, but I hope you've had some glimpse at least of where these equations come from, and so you'll not be looking for them. And the remaining time, I want to just introduce some very simple concepts on turbulence. And this is the last topic I will cover. It's not in your lecture notes. I decided to add this last night because I thought I might have a few more minutes, and I do. And turbulence, as you know, is an unsolved problem, and it's been so for over 200 years. But if you try to simply look at Webster's 1913 dictionary and ask what turbulence is, you'll say the quality or state of being turbulent, a disturbed state, tumult, disorder, agitation. That's a very nice qualitative concept that appeals to people. But mathematicians and physicists try to define turbulence in more precise terms. And you'll hear the word turbulence talked about a lot in these lectures as well. And this is Chorin's definition of turbulence, which is the distinguishing feature of turbulent flow is that its velocity field appears to be random and varies unpredictably. The flow does, however, satisfy a set of equations which are not random. Chorin kept in mind the Navier-Stokes equation, about which I'll say a few things in just a moment. For us, you could think of this as the MHD equations that I just described. Those equations, given a unique initial condition, will predict a unique final state, right? So the equations are not by themselves random or chaotic. But what is critical is that it has the appearance of being random. To make it more precise, if you err a little bit in the prescription of the initial state, the final answer can be dramatically different. It's that sensitivity to initial conditions that makes these equations have the appearance of randomness. It's the same thing that underlies chaos theory. You start out with Hamilton's equations, apparently simple-looking equations, but you change the initial condition of one charged particle a little bit, so the orbits in the final analysis are vastly different. It's this sensitivity to initial conditions that really distinguishes these sort of systems. And the equations are not random in themselves. So the fact that the equations are not random, but the predictions appear to be, is what is very interesting about turbulence theory. At a time, people in fact thought that if they understood chaos, they'll understand turbulence. When I was a graduate student, there was a big revolution which said, that's what you need to understand, and you would solve the problem of turbulence. I think that was a mistaken notion in history. Time has proven that. Chaos theory taught us something very valuable, but it didn't solve the problem of turbulence for us. And we are left still today trying to understand why the classic laws of turbulence theories are the ways they are, despite the fact that we've learned what chaos theory has taught us. So they share this common mathematical feature of sensitivity to initial condition, but that body of knowledge has not yet solved the turbulence problem. Leonardo da Vinci had an idea of what turbulence entailed. This is from he drew these large structures and small structures. In 1500, he was an amazingly smart guy. What I'm saying is nothing novel. Most of you know that. He was an amazing polymath, a great artist, a great scientist, a great engineer, all blended into one. And this sits in. But the notion that he's talking about here is what has been made more precise by the work of Kolmogorov. And I just want to go over some very quick ideas on hydrodynamic turbulence theory, because you will see some of these things will reappear in the lectures of Dr. Chandran and Dr. Casper to come in later. It's good for you to remember that MHD turbulence theory, as much as hydrodynamic turbulence theory, is an unsolved problem. And there are common features to them despite the discipline. So as Dr. Baker pointed out to you, it's very important to have this broad view of the connectedness of the various subdisciplines within space physics. I'm even pushing you further. I'm asking you to remember that fluid dynamics is a beautiful continuum from plasma physics, and some commonalities in disciplines there can be a very good learning exercise for us both ways. Though one cannot really translate all this terminology or the knowledge blindly, because systems are different and the results are different, but the mathematics has some underlying similarities. So this is Navier-Stokes equation. If you drop the Lorentz force term in your MHD equations, and you dropped all magnetic fields, and you assume that your fluid is incompressible, this is what you would get. Navier-Stokes is a special case of the MHD equations, with 1 over r as the Reynolds number. See, multiplying the second order spatial derivative in velocity, the same character in singular perturbation theory that I was emphasizing. Left-hand side, your first derivative, right-hand side, you have 2 derivatives. Be careful. And this is what is called the Reynolds number. Well, what Leonardo emphasized, but Kolmogorov made much more precise, is that turbulence actually couples large scales and small scales. The process of development of turbulence often starts at the large scale motion by the excitation of waves of long wavelength that quickly produces waves of small wavelength by a domino effect. And you have this gradual transfer of energy from the stirring scales. In the heliophysical system, it's the sun doing the major amount of stirring. Out comes from the sun plasmas, waves, that then interact, break up into smaller waves and eddies, and so you therefore churn in the solar wind a lot of what is turbulence. Lambda is the wavelength, k is the wave number. And I want to tell you that this process of going from large energies to small is really a very, very exciting problem in mathematics. Does this all happen in finite time? Through the ideal equations of Navier-Stokes, put viscosity equal to 0, blowing up, is called the Navier-Stokes existence and smoothness. This is a fundamental problem in mathematics that the Clay Mathematical Institute has actually suggested as a Millennium Prize problem. I don't suggest that you take this as a thesis problem. But someday one of you might solve this problem. NSF doesn't put a lot of money into this problem because it's much too fundamental. But the question that Navier-Stokes existence and smoothness tries to address is that if you start from a smooth initial state and you just integrate the Navier-Stokes equation without viscosity, or with viscosity, it doesn't really matter. Does the solution blow up in finite time? In other words, does it go to infinity in finite time? This is the existence and smoothness problem. Some of these things, at least one of them has been solved. A Russian mathematician solved one of these problems and never really reclaimed the prize because he thought it would be too corrupting. $1 million that somebody offered him. And he thought it would be so, I thought he should have taken the money and put it into his research. Why such a simple solution wouldn't occur to him, I don't know. But Schnirelman actually turned down the Clay Mathematics Institute prize for solving the point or a conjecture. But be that as it may, so there you go, in terms of aspirations and the larger life of mathematics and physics. What Kolmogorov did was essentially, through some very simple dimensional considerations, derived a spectral law that stands the test of time. In fact, simply argued that he didn't solve the Navier-Stokes equation. He made some hypotheses. he said the turbulence is isotropic in wave number space, which is writing energy as a function of wave number, and that energy moves from local interactions in K space. So he defined what he called an energy cascade rate as depending on K and EK with exponents alpha and beta that are unknown. Then he simply did dimensional analysis on this equation to derive what alpha and beta should be and predicted that the energy spectrum as a function of the wave number would be distributed in this manner, where Ck is a constant, 1.4 to 2 measured experimentally. Epsilon is the energy cascade rate. So the picture we have in mind is energy being stored in the large scales, cascading down to smaller scales, to larger Ks. And epsilon is a constant for the entire range, known as the inertial range, and energy following as k to the minus 5/3. This is the famous Kolmogorov k minus 5/3 law. What is really remarkable is that that law was derived for hydrodynamic turbulence, but has turned out to be a remarkably good description of magnetized plasmas in space. This is interstellar turbulence, the big power law in the sky, but people have actually taken the density fluctuations that they've observed and to see the Kolmogorov law valid for very, very large range of scales. The minus 5/3 law. Closer home to the solar wind, done by numerous people, but taken here from Goldstein and Roberts, and you'll learn more about this from Dr. Chandran's lecture, you also get this k to the minus 5/3 law. Why is the law that was designed for hydrodynamic turbulence describes remarkably well MHD turbulence is one of the big mysteries of turbulence theory. Nonetheless, it continues to be used. There's a lot of theory work and observational work that goes on this that still continues. I'm going to simply point to the fact that Justin Casper and Ben Chandran will talk to you about this. They will also put their work in the context of the Solar Probe mission, which is a mission that is precisely designed to address some of the issues of turbulence and heating that you will see later in the course. But let me just stop here. This was just a very rapid transit through some of the basic concepts in plasma physics that you might need to go through this course. More details you can find in any of the textbooks. I'll be glad to take questions. Thank you. Yeah.
You mentioned that the MHD equations often seem to give some decent results even when they have no right to. Where's like an example of where that happens, like physically?
So,
Can you repeat the question?
thank you. The question is that I mentioned during my talk that MHD equations often produce very good results when one expects they might break down. And when does that occur? To give an example where that might actually occur. So one example that comes immediately to mind is the Earth's magnetosphere. That's a very tenuous medium. And the MHD equation is derived under fairly strong collisional approximation. And yet if you calculate the simplest things about the mean free path of the system, you see often that it is much larger than the system size, not smaller. And yet MHD gives a remarkably good description of some of the larger scale motions. So what's the reason for it? Is this total fluke, or are there, after the fact, can we give justification to these things? So in the general area, the comment that I just made is true also. For example, of fusion plasmas, okay, which have gotten into higher and higher temperatures. And this very statement that the mean free path of the system often is larger than the system size also works there. Why does MHD often work despite that? There are a number of answers. Sometimes, if you have, even if you have low collisions, if you have strong magnetic fields, then the small Larmor radii of the system around small magnetic field kind of plays the proxy of collisions, if you will, keeping particles tied more to field lines. Even though collisionally they are not very strongly coupled. And this is true, for example, for laboratory as well as magnetospheric physics. And so you often find that global MHD codes may give you good predictions away in these large-scale regions where you would think they're seemingly collisionless. But if you go to weaker magnetic field areas where the Larmor radii become very large and the collisionless effects are really strong, you'll find the deviations becoming more and more significant. I can also give you an example where I think deviations from MHD would be very important, but they're not recognized as such so much because of the paucity of observation, and that is the sun's corona, for example, which is actually a lot denser and hotter than the Earth's magnetosphere. But if you calculate the numbers, though, you expect to see strong deviations from MHD occurring at small scales. But these small scales often fall below the resolution of spatial instruments. Solar physics is distinguished by absolutely gorgeous global images of the kind that Dr. Baker showed you on SDO, and the more of that you will see. But they often are very, very undersampled in narrow regions. Collisionless effects may be very important, but you're not seeing them as such. Does that answer your question? If anybody else would like to add to that, please do. Okay. Yes, please. Yeah. So this is what I was putting you in guard about. Oh, thank you again. She's asking, how does one know from first principles when to apply kinetic theory and when to apply fluid theory? You know, if you just stop yourself from applying a theory every time you start breaking its approximations, you may not learn useful things. So it's good, not a bad idea to sometimes push your luck with this and let observations be the ultimate determinator. But caution is well advised. So I would say check, be cautious, but don't be afraid to apply even, and you might be pleasantly surprised how well this works. And then you can go back and think, why is this working? And you might find some good reasons for it. Sometimes you get lucky. A lot of the times there are more hidden reasons beyond asymptotic approximation that we are able to grasp. You know, the plasma knows everything. It is us who are more stupid about our models. So keep that in mind with a certain humility and then apply your model, but be careful. So one of the things, thank you for asking that question. Her question is, can the kinetic model describe the magnetosphere? The answer is, certainly if you take the fully kinetic theory and apply it to the magnetosphere, you will say in some sense that's the word of gospel. But it's not very useful to say that, because one of the things that we learn a lot from, and something that I underemphasize in my code, is the tremendously important role that computation or computational science plays in our learning. I emphasized the nonlinearity of the equations, but I didn't emphasize that it is because of this that analytic models sometimes run short and we have to rely on computation. So suppose if I then said, can I make a completely kinetic magnetosphere? It's not within the reach of even exascale computers, forgetting about the pettascale or any time near the near future. That may be the final word, but that's not going to be achieved in your and my lifetime. Not only that, it may not be one that you want to do for every problem you want to solve, because that may be too much information, more than you can possibly store, test, or have use for validity. So, therefore, I would say that the proper way to go about thinking about this is that think of the problem first, or what the observations are treating you. Every theorist should start from that. Then try to make up a model with various ingredients that could have fluid in places and a more sophisticated and more detailed description in some other places, and then patch together a description of that phenomenology that will allow you to come to an understanding of it. Because there is nothing like the Holy Grail here that is within reach. We cannot do a fully kinetic magnetosphere, but we possibly get to the point where we can do a global effluid magnetosphere with more kinetic understanding of the smaller layers. This too is not an easy problem, computationally especially, and is now a frontier problem that many people are trying to address. People who want to do it purely by fluid equations are trying to design better equations of state as starters, something that some of us are thinking about. Yes?
Yeah, if we accept the Kolmogorov sensible framework for turbulence, what is exactly the static
Oh,
of turbulence?
so I should draw a picture. Classic Kolmogorov picture is like this. E is the energy contained as a function of K, and the picture is very cartoon-like. Looks like this. This is what is called a stirring scale, or the large scale. Okay? Local interactions in K-space means neighboring interactions in K-space. And the energy comes down in a light from large space to large. And here is where your viscosity, or for collision-less plasmas, kinetic effects take so long. This is what we're plotting on.
But for plasma turbulence, at one point you don't have heating in the entropic sense,
So
right?
this is a really important question. For Navier-Stokes turbulence, this is set by viscosity. For plasmas of the kind that you see in the solar wind, where either viscosity or resistivity are often way, way further away, what this does is typically controlled by kinetic properties of ions and electrons. And oftentimes this so-called region is not all heating. What you have is, for example, in the solar wind, this is shown, measured to be set by the so-called ion skin depth, C over omega pi. Further down is what is the electron skin depth, C over omega pi. Just because there is a break in the curve here at C over omega pi, it doesn't mean from here onwards everything becomes heating. In fact, there's a new scaling law that begins, which is more controlled by ion kinetic theory. And the dissipation might be postponed until you get to the electron scale. Observations recently done in the solar wind, which you hear about again in Dr. Chandler's lecture, actually seems to suggest that a lot of the heating is actually occurring in the electron scale, a phenomenon called Landau damping that some of you who have taken plasma physics know about. The energy coming from the large scale is getting all the way to electrons. But does it get all the way to electrons? Do they already start hitting the ions at a larger scale? Again, an open question in solar wind turbulence. One that will get addressed more and more is getting addressed already with cluster mission, but will also get addressed in much more detail by Solar Probe Plus. Solar Probe Plus, which will go closer to the sun than any mission before, is supposed to teach us something about the heating of the solar wind. And this is where questions like yours are very important. Yes, please.
For which time and space scale one can say that the frozen ring theory is valid?
Typically for scales that are, thank you again. How many times do I need to learn this lesson? Mr. Hayes to answer. Her question is, over what length scales is it okay to assume the frozen in law or Alfvén's theorem holds? So this will seem like a little tautological, my answer, but all scales that are much larger than the very narrow scale over which magnetic diffusion becomes important.
Do you have any examples for
Sure.
solar,
In fact, I just wrote down the ion skin depth there for the dissipation range. You will find that will reappear in the collisionless magnetosphere. So for scale lengths that are much larger than the ion skin depth, and certainly a lot larger than the electron skin depth, which is smaller than the ion skin depth, MHD is not a bad model for large-scale motions. And one can actually justify that on mathematical grounds. So when I say breakdown of MHD, I am actually overstating the case a little, because over that scale, much larger than the ion skin depth, MHD is a very good approximation. It starts breaking down over that interesting narrow region, where the second derivatives that I was talking about in the induction equation, take as an example, can be very, very important. That's where current densities tend to peak as well, and so on and so forth. So that the eta J term on the right-hand side of Ohm's law, if you are dealing with a resistive plasma, becomes very important. If it is a collisionless plasma, that's not so important, but other terms in Ohm's law that I'll talk about and Dr. Rayleigh will talk about become very important. Further questions? If not, I stand between you and lunch, and this is not very tenable. Enjoy your lunch, and thank you all very much for your attention.